Greetings to all and welcome to this lecture. We are in module 9, lecture number 5, polysilicon depletion. In this lecture, we will discuss about polysilicon depletion and how this polysilicon depletion influences the CV characteristics. These are the learning outcomes of this lecture, which helps you to understand the mechanism of polysilicon depletion in MOSFET and the impact on gate electrostatic. When the gate metal is replaced by polysilicon, then it influences the potential and charge balance of the surface. That is what we are going to see in terms of some electrostatic equations what we have already derived into terminal MOS structure. Let us do a quick recap. In previous lecture we were discussing about hot carrier effects. We said that when the channel length of the MOSFET is very small, then the carriers are velocity saturated throughout the channel, and these high velocity comprising electrons, when they leave the source, they move towards the drain. Ultimately they encounter this abrupt junction between body and drain. At that junction the electric field is so high, and hence the randomized component of the velocity is increased. So these carriers are called hot carriers. Now when these hot carriers will strike to the silicon atom, they will create electron hole pair. This is called impact ionization. So because of this electron hole pair generation, the electron stream go towards the drain side and hole stream will come towards the body, because body is connected either to ground or connected with a negative terminal as VSB. So this whole movement towards the body from the drain will give you a current IdB, and the electron movement which is going towards the surface is nothing but including into the main stream of the electrons which is coming from this side, give rise to a current IdS. So we can say that IdB is directly proportional to IdS. We derive a closed form equation with some assumption that the electron which are coming from the source is having a laminar flow and exactly parallel to the surface. The second assumption is there was only a primary impact ionization. It means there is no scattering or no impact ionization happens because of these EHPs. With this condition we said that there is IdB flowing. Now in MOSFET, if there is a drain to body current which is flowing inside this side, and this is N plus, this is N plus, this is P type body in NMOS, then there will be a significant potential drop in the substrate. And because of the inherent bipolar junction property, this can be considered as emitter, this can be considered as base and collector. There will be a positive feedback occur and we will get a snapback action. We have shown the IdS VDS characteristic as increases and there is a sudden increase in the current. Accordingly, because of increase in IdB, there is also a channel breakdown. We have also discussed about ballistic and velocity overshoot impact, where we said that if the channel length or the dimension of the channel is comparable to the mean free path of the electron, meaning the electron is not undergoing with scattering event, and hence the velocity is higher than the drift velocity. That is what is velocity overshoot. And in the ballistic transport we said that we can model the ballistic transport by just changing the drift velocity by effective velocity. So this is all about short channel geometries what we have discussed, the additional effects. Now let us see the another short channel effect which is significant when the oxide thickness is smaller, meaning you have an oxide thickness, you have an MOSFET having a very thin oxide thickness. In that case, generally we prefer to make a gate instead of metal, we will use polysilicon, which is a highly doped semiconductor. Highly doped semiconductor. So to say, saying the polysilicon as a metal is incorrect. It is a semiconductor with a heavily doped. but in some cases we cannot dope the polysilicon so heavily, and because of that the polysilicon gate is getting depleted. It is same as the surface depletion which we have discussed in 2 terminal MOS. So, polysilicon is a widely used gate material in MOSFET. However, it is not a metal, it is a semiconductor. So, all the electrostatic what we have discussed so far, like depletion, inversion, accumulation, it will happen inside the poly gate also. In general, if we do have NMOS, then the preferred poly gate is of N type semiconductor, and if it is PMOS, then preferred poly gate is of P type. So, let us consider an N type semiconductor, or we can consider a 2 terminal structure where my substrate is P type. So, obviously this is a foundation for NMOS. This is an oxide having thickness TOX. The capacitance associated with is COX dash if we represent in per unit area. Now, instead of metal gate we are using a poly gate. So, this is a poly gate. Now, this terminal is G and this terminal is B. We are using same notations what we have used in 2 terminal MOS structure. Between G and B we are connecting a voltage which is called VGB, and we have discussed how the connection of positive voltage in the gate to body causes depletion and inversion in the surface and give rise to a potential psi s, which we called it as surface potential. So, first there will be a depletion and then there will be an inversion. In that condition the gate was metal, however, here the gate is made up by polysilicon. So, when you apply the positive voltage, the positive charge coming at this surface requires is actually pulls the electron toward this side, and hence this surface is getting depleted. As it is N type semiconductor, the depletion will give you positive ions. So, this depletion is called polysilicon depletion, or in general poly depletion. Now, what is the impact of this poly depletion in the electrostatic of the surface? That is very important, because when you put this 2 terminal structure in our MOS transistor and there if the polysilicon depletion happens, then definitely it will affect the surface condition, and in turn it will affect the device current. So, let us see how we can rewrite the potential balance equation for this polysilicon. You remember that we said a potential which is exactly from the surface to deep in the body is surface potential. We denoted by psi s, and if VGB is positive, the surface potential is positive, like this. Similarly, there is a potential drop across oxide, we called it as psi ox. Again, the polarity of this psi ox is positive and negative. Now, the 2 ways you can think of what is the polarity of psi poly. One is the potential which causes this positive charge to come near the surface, right, should be negative, and hence this will be positive. The another way is when you apply a KVL, the total drop should be positive and negative, correct. That is what the sign convention of these different voltages are: positive, negative, positive, negative, positive and negative. And when you write a KVL to find out the total potential balance equation of this system, you will get this, where it says that when you have a VGB as an external voltage, then the potential drop will happen in polysilicon depletion layer, in oxide and in surface. So, let us consider this is an oxide. Moreover, we do have an additional drop which is across the contacts. So, this voltage is psi s, this voltage is psi ox, and here there is a polysilicon depletion. Because of that, the polarity of this voltage is also plus and minus psi poly. We remember that additional voltage drop at the contacts, which is nothing but the difference of work function of metal and semiconductor. So, we can rewrite this equation as VGB is equals to psi poly plus psi aux plus psi s plus phi ms. In two terminal MOS, when we were considering the metal as a gate, this term was not there, and the total potential balance equation was VGB is equals to psi aux plus psi s plus phi ms, where VGB is an external voltage. Now, in this condition, the charge balance equation will also change, right? The total charge in the system should be conserved, and hence you will get Q poly dash plus Q I dash plus Q B dash plus Q naught dash is equals to 0, where these three quantities are known to us. This is inversion charge in the surface, this is bulk charge in the surface, and Q naught dash is an oxide charge, which is we have considered as a fixed oxide charges and always positive, fixed oxide charges, right. The charge Q dash poly is nothing but this depletion charge, right. Now, how can we relate this charge and the potential drop across the poly? We can simply write the same equation which we have written for relating the equation of QB dash, which is nothing but bulk charge, and psi aux. So, we said that QB dash is equals to psi aux into C aux, right, and this charge is negative. However, if you do have a parallel plate capacitor, you can take any charge to write the equation. Similarly, Q poly dash is nothing but COX dash into gamma into square root of psi poly. That is what it came from the previous equation as QB dash is equals to minus gamma COX dash square root of psi s. Many a times we have used this equation for bulk charge. However, there are two differences. One, this psi poly is the poly potential, the potential across the poly region. The second, we do have positive charge now, because QB dash was the charge representing at the surface, which is a depletion charge, and it was a negative immobile ion. However, if the poly gate is of n type, then the charges are positive. So, you can simply write COX dash into gamma into square root of psi poly. Again, the gamma is a body effect coefficient, which is nothing but 2 into Q into n poly into epsilon s divided by COX dash, correct. So, here we should have n poly, it means the doping concentration of poly region, whereas here we have taken gamma is equals to square root of 2 into Q into Na into epsilon s, where Na is the doping concentration of this substrate or body, which is p type, and obviously this n poly is nothing but Nd, a donor type. But just to get a differentiate between n poly and Na, we are using n poly here. So, I can simply write the charge equation as square root of Q into 2 into Q into epsilon s n poly into square root of psi poly, where these all are known quantities now. Now, can I calculate the capacitance for weak inversion? Now, if you see the whole system, we do have 6 variables to play with. Earlier, the variables was Qi dash, Qb dash, then psi s and psi aux, and we derived or developed our complete MOS theory based on these 4 variables. However, now when we introduce the polysilicon, then the 2 additional variables are coming into picture, which is Q dash poly and psi poly. Now, what is the influence in the capacitance when we considered about the polysilicon depletion? You see, in a layman word you can understand like this. Earlier you have a capacitance like this, where this is a metal plate and the charge is here. For single positive charge there was a negative charge which was either given by bulk charge or the inversion charge, and accordingly we said that how we derive a MOS cap, how we derive CV characteristic, correct? This is COX dash, this is CGB dash, and this is VGB. Now, when you introduce the polysilicon layer, the polysilicon depletion region is expanded in the polysilicon gate, and hence because of that the overall capacitance is reduced, because the thickness of polysilicon gate is coming into picture, meaning the expansion of this polysilicon layer is increase the separation of these positive charge which you applied through VGB and the negative charge which is coming near the surface. So, the distance of the charge or the separation of the charge is increased, and hence the capacitance which will reduce. That is what this dotted line shows the capacitance when metal gate is used, and there is significant reduction in the capacitance when poly gate is used. Now, let us see how this system affects the operation of MOSFET when we operate the MOSFET in either weak inversion or strong inversion. Let us discuss first about the weak inversion. We know that in weak inversion the gate voltage is such that you have depletion and just you are at the boundary to create inversion, correct? At that condition we can comment on threshold voltage. Now, consider that Qi, this will be Qi. So, consider in the weak inversion Qi dash will be approximately 0, and hence in the system what we made as a MOSFET with a polysilicon gate. So, this is an oxide, this is poly, and here you are making a N plus and N plus region, and this is substrate or P type. In this system the two charges are left when you applied the gate voltage in such a way that you are in weak inversion. So, here there is negative charge and here there are positive charge. Across this oxide the charges are balanced, right, and hence you can simply write Q poly should be equal to minus of CB dash or QB dash, right. Q poly is equals to minus of QB dash, considering the inversion charge goes to 0 in weak inversion. Now, we can use the previously defined formula. Q poly can be given by square root of 2 into Q into N poly into epsilon S into square root of psi poly should be equal to negative. So, negative and negative get cancelled, 2 into Q into Na into epsilon S into root psi S. From this equation we can compute that square root of Na into square root of psi S is equals to square root of N poly into square root of psi poly, which will give you psi poly is equals to Na into psi S divided by N poly. So, we can simply relate the surface potential or the potential across the poly depletion is equals to the surface potential across the surface and multiplied with a ratio of their respective dopings. Now, how can we comment on the capacitance of this poly? We can simply do a derivative of charge with respect to voltage. So, C is nothing but dq by dV, meaning the charge was square root of 2 into Q into N poly into epsilon S into root psi poly which will give you square root of 2 into q into n poly into epsilon s divided by 2 times of square root of psi poly. Now, can I represent this term in terms of Cb dash? Yes. So, you just bifurcate this part as square root of 2 into q into epsilon s divided by 2 into square root of n poly divided by square root of psi poly. This is nothing but equal to C dash poly, where C dash is nothing but capacitance per unit area. Now, if we write the equation for Cb dash, which is nothing but square root of 2 into q into epsilon s divided by 2 into square root of Na by square root of psi s. So, this quantity can be replaced in terms of Cb dash square root of psi s divided by Na. You put this equation here and ultimately you will get C poly dash is equals to Cb dash into root psi s by root Na into square root of n poly divided by square root of psi poly. From the equation 1 we derived the relation between psi poly, psi s, Na and n poly. You can replace here, ultimately you will get that C poly dash is can be given by n poly divided by Na into Cb dash. So, this is a relation which helps you to understand how my capacitance across the depletion region of polysilicon gate is related with the bulk capacitance. Now, if you closely see the overall capacitance in previous cases when the metal gate was there, then the overall capacitance was series combination of COX and the body capacitance, we generally said Cb dash, right. But here in weak inversion when Qi is negligible, then the overall capacitance which are in series is Cb, Cox and C poly. So, let me define a new capacitance which is a combination of Cox dash and C poly to get the equal effect of these capacitance at the surface, and hence we can write this equation as total C poly oxide, meaning you are including the capacitance of poly and capacitance of oxide is nothing but a series combination to show a single capacitor, which is C dash poly ox is equals to 1 over C poly plus 1 over C dash C ox dash, which is nothing but these two capacitance are in series. So, this is polysilicon layer, this is oxide layer, correct. Now, can we comment on the effective oxide thickness, because as we know the polysilicon depletion increases the effective oxide thickness here, because when the polysilicon layer depleted, then the capacitance is reduces, and hence we can say the effective oxide thickness is increases. How can we do that? Let us define the thickness of this, the combination is TOX cap, right. So, we can rewrite this equation in terms of permittivity and thickness as TOX cap divided by epsilon OX is equals to this C poly can be written as C epsilon S into D poly plus this can be written as TOX divided by epsilon OX. Make sure that when you are writing for C dash poly, you have to take the permittivity of semiconductor, not the oxide, because the poly is a semiconductor. That is what I have taken epsilon S here. So, if you want to find what is TOX dash, it means what is the effective oxide thickness of that particular combination of C poly and C ox, or the poly depletion and the oxide thickness is can be given as D poly into epsilon OX divided by epsilon S plus TOX. And now, if you want to find out the change in the effective oxide thickness or the change in the oxide thickness is nothing but delta TOX, which is nothing but given by the first term, because the second term was nothing but the oxide layer thickness, which is TOX, correct. Now, the one good advantage of polysilicon depletion region is that it increases the effective oxide thickness, which is very much beneficial when the oxide is thin, and that is what the idea to cover this topic here under short channel effect, because ultimately reducing the dimensions is not only reducing the length or the width, you are actually scaling down the dimension in all, scaling down the MOSFET in all dimensions, right. That is what, if you reduce down the TOX, then there will be other effects come into picture, and one of the possible solutions is use polysilicon gate. Now, can we comment on the slope factor? We know the slope factor can be given by 1 over C B dash divided by COX dash. The slope factor decides the subthreshold swing when MOSFETs is considered, right. We have decided that this is nothing but d psi s divided by dVGB inverse when we were discussing about two terminal MOS. However, there is a catch. Now, we do not have the oxide layer only, we do have a combination of poly gate also. So, C poly also. So, ultimately, if you want to calculate what is the gate control in the surface with respect to this oxide, right. So, you need to rewrite the equation as 1 plus CB dash divided by C poly ox. That is what we have derived in previous slide, that this is the effective oxide now, correct. So, ultimately this is the equation. Can I find out what is the equation for CB dash by C poly? So, N is equals to 1 plus, you go back to this equation and see, I am interested in CB dash divided by C poly, right. So, I can simply multiply in the numerator by CB dash, I can get this term can be written as CB dash by C poly dash plus CB dash by COX dash, right. So, if I want to compare how much increment is there in the slope factor, we can simply say delta n is nothing but by this amount CB dash by C poly, it is increased, right. The slope factor is increased by this amount when you use polysilicon depletion. And now again we can replace by CB dash and C poly by equation what we have derived here, right. So, CB by C poly can be written as what? Na by N poly. So, you can simply say the slope factor is increased by a ratio of Na by N poly, correct. Now, we will see how this polysilicon influences the strong inversion behavior. In strong inversion, the surface potential is pinned, and we can rewrite the equation for inversion charge as minus COX dash into VGB minus VT naught, where VT naught was the extrapolated threshold voltage. However, when the polysilicon gate is coming into picture, the gate is fighting against that voltage to deplete the surface, then invert the surface, and also to deplete the polysilicon layer. That is what the threshold voltage which was discussed earlier in two terminal MOS, when the metal gate was used, there is additional term will come psi poly, because this voltage what you are applying externally is also depleting your polysilicon layer, right. So, that is what you can rewrite this equation as VT naught cap plus VT naught into, again psi poly can be replaced by this equation, right, to get a form of equation in terms of doping. So, VT naught is equals to VT naught plus Na divided by N poly into psi s, where psi s is nothing but phi naught, right, in strong inversion. So, what polysilicon does is it reduces the inversion charge, because the threshold voltage is increases. If the threshold voltage is increases for a given gate voltage, then the inversion charge reduces. It reduces the effective gate capacitance, because the additional capacitance is coming in series. It increases the effective oxide thickness. So, in that sense, yes, polysilicon layer deposition is a good idea, because when the oxide thickness are very thin, right, then you can use the polysilicon gate to increase the effective oxide thickness. So let me summarize that in this lecture we have discussed that what will happen if the gate is replaced by a polysilicon gate. We found that when you replace the metal gate by a polysilicon gate, then the polysilicon depletion will occur. This is similar as how we see this is similar as how we saw in two terminal structure. When we are applying a gate voltage, then this gate voltage is depleted the surface and then it causes an inversion. Similarly, when you apply a positive voltage, it will deplete the polysilicon and therefore it increases the effective oxide thickness, meaning the gate control loses its control and hence the threshold voltage increases. The increase in threshold voltage in strong inversion causes reduction in inversion charge for a fixed gate to body voltage. There is one more thing, if you increase VGB beyond a point, then there is also a polysilicon inversion happens, right, which we are not considering here. That will happen when you increase VGB beyond a certain value, then there will be a polysilicon inversion happen, means the holes will come near the surface and there is an electron and hence the capacitance will increase beyond a certain VGB value. So we will stop here for today. Until then, take care.